here's our car. It's sitting still. And we have our thing hanging from the rearview mirror. How many of you can imagine this scenario? You can imagine being in a vehicle. The vehicle goes, you slam on the accelerator and the thing swings backwards towards you in the car. The reason why you tend to have difficulty with this problem, for those of you who are having difficulty with it, which is probably quite a few, is perception. The dice never swing backwards. You think they swing backwards because you're in the car. But it's not like the dice actually went backwards. The car went forward and the dice tried to stay in place because they have inertia. I'm saying dice because I used to put dice there, but nobody puts fuzzy dice on their mirror anymore, so I just had to pick something. But I'll keep saying dice because I'm programmed to say so. I'm sorry. But again, it wasn't that the dice went backwards. The dice had inertia. They tried to stay in place. The car went forwards, and they could not begin to go forwards until there was an unbalanced force acting on them in the direction of the car. So what happened? Well, the car began to accelerate forwards. The acceleration of the car is in this direction. So the car is going to move to the right, but the dice want to stay right here. You are in the car with the dice. So you believe the dice have shifted backwards. They came towards you, but the real thing is the entire car moved this way. The dice just stayed in place. And they stayed in place until such time that the tension in the string caused them to accelerate. So, the moment the angle between the dice and the vertical wasn't zero, there was a component of tension in the direction of motion, and then the dice could start to move forwards. I'll say that again because I think it's a valuable piece of information. The moment the dice no longer made an angle of zero, they weren't completely vertical, the moment they started to make an angle, there was a component of the tension in the direction of motion. And it was that component of the tension that caused the dice to move. To understand that and appreciate that, this is the direction of the acceleration of the car. My free body diagram of the dice should begin with weight downwards, but there should be a tension that's at an angle. It's not accidental, although that's an accident. It's not accidental that I made the tension greater than the weight. The tension is going to be greater than the weight. The tension is now serving two functions. One function is to keep the dice from falling to the floor. The second function is to accelerate the dice horizontally. Now, either way, those are the only things touching the dice, the only things acting on the dice, so we have our free body diagram. Our next step would be to draw a coordinate system. And this is a place where students continue to make mistakes because they're not thinking through what's happening. Your coordinate system here should be aligned with the direction of the acceleration because our dice are part of the car. They are accelerating. The net force in the dice is not zero. They accelerate with the car. So, I would expect you to make your positive x direction to be the direction that the car accelerates. Again, I know a lot of you think the dice accelerate backwards, but they don't. You, the dice, and everything else in your car is accelerating forwards. Yeah.
Would there be an interface?
Is there a surface touching the dice? Is it in contact with any surface?
The string?
The what?
The string?
The string provides tension. Right? The string can't push on the dice. It can only pull. So I'd argue that we now have a fine coordinate system. Our job is to break the tension up into its components. So I'll have a component this way and a component this way. This angle will be theta, the same as this angle. For reasons that I think are obvious, but maybe not, alternate interior angles would be the reason that these two angles would be the same. Way back in the geometry. This side is t cosine theta, and this side is t sine theta. I have no trouble with my trig. Make sure you are working on your trig. Net force equals ma in the x direction, and net force equals 0 in the y direction. There's only one force in the x direction, and that's t sine theta. That equals ma. Now look, I know that I can sometimes make this look easy, but I understand that for many of you, there's a lot of steps here. Knowing that you were going to take the tension and create, a component that had t in it, some of you are still probably wondering where t sine theta came from. If that's you, and you're not asking questions about how I'm getting these values, don't think it just spontaneously happens for students. It takes practice, and it takes probably more work than I'm showing. It might take you putting that this is the opposite side, this is the hypotenuse, this is the adjacent. For the first time ever, a student finally asked me a question that I did not anticipate. Meaning, they always ask questions I don't anticipate. A question I had not thought about before as being a problem. But I had a student who didn't understand that arrow was actually an arrow that represented tension. They could easily identify it as a hypotenuse. They couldn't make the mental leap that the hypotenuse was a vector for tension, and therefore was part of their geometry. They could say sine of theta equaled opposite over hypotenuse, but they couldn't replace the hypotenuse with tension. And I don't know if this is you, and I'm mortified that I'm actually doing all of this, but I have to take the students as they come to me. So this is where all that's coming from. I'm just not writing it out anymore because I don't want to. So in the y direction, I have t cosine theta minus mg equals 0. So we're done with the Newton's law portion. It generated my two relationships that I could use to figure out, at this point, anything I'm being asked. I think they want what the acceleration of the car is, right? Is that what they're looking for? I don't remember the question.
Is this the angle the mass makes when the car travels at a constant velocity?
That's a secondary question, right? Okay. All right, so let's just solve this for acceleration then. Would that make sense? If I want to solve this for acceleration, I'm going to probably do this a way that I hope makes sense, but it might be different than what you would do. Whenever I see something like this, something where there's clear, symmetry. I see some symmetry here, right? T sine theta equals ma, t cosine theta equals mg. They both have a lot of similarities. So I'm going to stack the two equations, and I'm going to divide both equations by each other. It's like dividing the same thing on both sides of an equation. I'm going to divide the left side of the equation by t cosine theta, and the right side of the equation by t cosine theta. But t cosine theta equals mg. So on the right side, I'm going to write mg and not t cosine theta. But I'm really just dividing both sides of the equation by t cosine theta. And when I do, that gives me kind of a new formula. I'm doing that because I notice that if I'm careful about this, the t's cancel and the m's cancel. So it doesn't matter what I hang. as long as the cable doesn't break, the acceleration equals g tangent theta. Now, I hope you notice first that this could be a way to create an accelerometer, right? A cheap accelerometer would be a protractor with a weight hanging on it. You would just look at it when you're accelerating. You could glue it to the ceiling of your car. And as you looked at the angle, you could figure out what your acceleration is for your car. It is a very inexpensive accelerometer. In fact, they used to put these on some rides at Busch Gardens as their accelerometers. They usually use little balls on chains inside tubes, but they could do this just as much. But it also tells me pretty simply that if the acceleration of the car was 0, the angle has to be 0. Right? If I put 0 in for acceleration, the angle that would correspond to that would have to be an angle of 0. So when the car is traveling at a constant velocity, the thing should just be hanging there because the acceleration is 0. Meaning the thing on your rearview mirror only moves when you're changing speed or changing direction. It doesn't move any other time. It stays straight down. And that should be pretty true for most of you who've ridden in vehicles. Stuff only seems to be moving around your car when your car accelerates. When you're moving at a constant velocity, everything in the car feels like it just stays where it's put. Because it normally does. Unless you hit a bump or something. All right. I discussed the idea of the coefficient of static friction and the coefficient of kinetic friction 2 days ago. Then we had our little interlude yesterday where I taught you computer things. What I would like you to do is use this today. And I want to see if you can with a sample question. The first sample question is pretty easy. I think you guys could probably do it because you've already done it. The coefficient of static friction between tires and the road is about 0.8. What is the maximum bank angle that a road could be banked before a car would slide down the embankment? Meaning, if I was trying to design a roadway that's going to have the road banked. You guys have ever been on a banked roadway? Like all the overpasses and stuff, the roads are all kind of tilted at different angles. There's a reason they do that we'll get to shortly. But what is the maximum bank angle? So if your car is that's your car that we're looking at from the back. There's a license plate. That is a car, I promise. And we're looking at it from its back and it's driving away from us down this banking angle. If the coefficient of static friction is 0.8, what is the maximum angle that we could bank the road without the car sliding down the ramp? This is a coefficient of static friction question. I like it because it uses static friction, which means it's going to be using the idea that there's a threshold in our problem. And I think you could probably imagine that this problem is a Newton's first law problem because we don't want the car to slide. So we expect that the forces on the car will be balanced so it won't slide. I don't want to do this problem. I want you to do this problem. But let's start by doing this problem in sections. And section number 1 is recognizing that this is still a force problem. So could you analyze this problem and work the force problem until you have friction equals and normal force equals? You should be able to. So I'll wait patiently, but I want to walk around and see those two things. And I'm going to give you 60 seconds to do so, because it shouldn't take long. I'm not going to spend a long time doing the inclined plane portion of this problem, because we've kind of already talked about those, and I'm kind of on the hopes that I don't really have to do it that much. Weight. Normal force. And I'm thinking, as I look at the normal force and the ramp, that to keep the car from sliding suggests that friction would have to be this way to try and keep the car from sliding down the ramp. Are there any questions about why I made any of these choices? All right. Even though this is a Newton's first law problem, I still think it best to align my x direction with the ramp. It doesn't matter what direction I make positive x, but it's not accelerating, but I need to make at least one of them the positive x and one of them the positive y. The weight's going to have two components. And the fact that I walked around and I saw a lot of you just barely starting to draw your free body diagram means you probably just didn't know where to even begin. And that's kind of bugging me. We've done ramps before. This problem is no different. And I'm also jumping down the idea that this is mg cosine theta. This is mg sine theta. Look, commit it to memory. It'll be faster. Even if they change up the problem a little bit, at least commit this part to memory so you can kind of blow through it. Because I see net force in the x direction equal to 0. It's got to be friction minus mg sine theta equals 0. And net force in the y direction, which equals 0 as well, it's got to be normal minus mg cosine theta equals 0. Yes, sir.
How would you know which axis to do the angle? Like for example, why wouldn't you draw the angle coming from the y? I want to draw it from the y.
First, I've answered this question before. And I've answered this for you before. So let's write this down. Okay? The easiest way to know where to write the angle, if you're setting your coordinate system up in this way, is continue the normal force onto the other side of the ramp. Right here. The angle goes with the whatever you're using for your y-axis, if it's aligned with the normal force and the weight. That's where that angle goes. And that will be the angle of the ramp. Every time. Just continue the normal force onto the other side of the ramp. Even here, continue to the other side. It's going to be the part that connects that with the weight. Okay? Every time. So, at this point, what I asked for was for you to solve for this. A few of you smugly went further than this, but I wanted you to kind of wait, not because I didn't think you were capable, because of what you did next, which was not necessarily what I wanted you to do. We want to find out what the maximum angle is. You need to know whether what you have mathematically proves it's a maximum or not. If you have anything that says theta equals, you're wrong. And it's not because I don't think you're smart, it's because you're not doing what I asked. You don't know if it's a maximum or a minimum. So you need to prove to the person grading your test that what you have is a max or a minimum. And that person next will be me. So friction is less than or equal to mu times the normal force. When you sub, anytime you're dealing with an inequality, you have to sub into the inequality. I brought that up 2 days ago, but here's another example of it. We substitute into the inequality, which means friction there, normal force there. And that's because it's an inequality. We can't substitute out of the inequality because we don't know what side it has to be on. So I'll have mg sine theta has to be less than or equal to mu s mg cosine theta. Now you could solve this for theta, or more importantly, you could solve this for the tangent of theta. So I cancel out the mg's, and I'll get tangent of theta must be less than or equal to mu s. Well, that means that it can't be greater than whatever I get for the value when this is an equality. So it is looking for a maximum. You could go one step further and say tan theta max would be when this is equal. But you have evidence that it's a maximum and not a minimum, because you have your inequality. And yeah, I'm not going to put the 0.8 in and find out what the angle is. I don't care. Right, I've now solved it for all of those questions. So try to put your numbers in last, and it'll be better for you. This is how we use coefficient of static friction. There are other questions related to this, and I'd like to try some. Are there any questions about this one? Then try this one. As examples go, there's nothing more to teach about friction. You just need to see examples. And so for the time being, I'm sticking with kind of what I would call the low-hanging fruit of examples. None of these are particularly interesting or hard, but they at least show off different kinds of problems. And here's the next one. What if I have a rope connected to a box that can apply a known force F at an angle of theta? Box has a mass m, and there is a coefficient of static friction mu between the box and the ground. Now, can you find an expression for the force? No, I'm sorry, let me see this different. I'd like an expression for the minimum force necessary to break friction. I want the minimum force necessary to break friction. Now I think this question is tough because it's hard to know where to begin on this one. I mean, obviously it's a force question. So obviously you're going to be drawing a free body diagram and making your net force stuff. The real question comes down to, is this a net force equals 0 problem or a net force equals MA problem? Which one would you choose here? We are looking for a minimum force. So I don't need the box to accelerate. I just want to break static friction. So I think we're looking at a net force equals 0 problem. But the moment I break static friction, kinetic friction will take over. So I don't know if the box will accelerate or not, but I want to find the threshold. Where's the point where the box breaks free? So I'm really looking at what is the maximum force I can apply before the box breaks free. Anything more than that, and the box breaks free. I think you should still start with the free body diagram. But we've done this problem before. We've done a free body diagram with friction and a force at an angle. So you should be able to just kind of make one of those happen super fast. Is this what yours looks like? That's what mine looks like. I didn't use a ruler or nothing. I'm in a hurry before the bell rings. I see people still drawing, so I'm going to wait a second, but I'm going to go ahead and at least start putting the coordinate system together. And I know it's a net force equals 0 problem, but I'm still going to make my coordinate system look like that. And I'm thinking something like that. So F sine theta, F cosine theta. Now this problem is actually got some challenge to it, but I would expect that nobody would be challenged to getting to this point. Everybody should be able to get here without difficulty. In fact, I'd argue that getting here also shouldn't be too terribly difficult, because we've done stuff like this. Can we all get to there? To me, this is the minimum requirements to be able to at least start the analysis. Any question about what's happened so far here? Are we sure? Because if you can't do this, you can't go on. So I can go on? Or am I waiting? Because I'm okay to do either one. If that's a hand in the air, you're going to have to do better than that. Go ahead. Oh, it wasn't? Okay. Then it wasn't. Excellent. All right, let's move on. I don't know what the conditions are, but I know that this is a static frictional problem. So I'm probably going to have to work in this, at least at some point. Now's as good a time as ever, right? We want a condition. We want F. What force is necessary to get the object to start moving? And I have it in two places. If I solve it for one, it's still in the other, so I need to bring them together. And like I said to you before, that's one thing friction can do. It can bring two sides together, because friction brings the normal force and the frictional force together. If you haven't put this in your head or haven't put this in your notes, remember, friction will always be perpendicular to the normal force. So they will always be in different parts of your formula. But the equation lets you bring those two formulas together. So I'm going to solve this for friction. Plug that in there. I'm going to solve this for normal. Put that in there. I don't know that you would have thought to do this. Some of you did, I'm sure. But I know some of you, no. But this is what I mean when I say you've got a third piece of information, use it, and if it's a problem like this, where there's a threshold, plug into your inequality. It will help you move along with the problem. So now that I've done that, I can say, all right, I'm just trying to get myself some space. Looks to me like F cosine theta must be less than or equal to mu s times mg minus F sine theta. Whew, that's a lot. That's a whole lot, isn't it? And we're not done yet. You're supposed to solve that for F. I wanted what would be the size of the force necessary to move the box. Can you solve that for F? Some of you can. I would probably start by distributing the mu. Boy, a lot of alphabet soup here, right? Letters everywhere. Everybody loves having numbers in their problems. This is probably why. I see an F here and here. So I need to get them on the same side. So F cosine theta plus mu s F sine theta equals mu s mg. Got them on the same side. It's not equals, it's less than or equal to. Well, I can factor now. Can pull out the F. I'll get cosine theta plus mu s sine theta. It's less than or equal to mu s mg. Whew. Almost done. Boy, this has been a lot. This is not the answer. This is what we get by following the process I've been telling you about. You have to interpret the answer. So first, I know a lot of you, this is a lot of algebra. And I don't apologize for it. There's nothing here that you haven't learned. There's nothing here that's more than just simple adding things to both sides and dividing from both sides. I get there's a lot there, and I get for some of you, you've never done anything like this in a long time or ever. I don't care about any of that. It's not that big a deal. You'll just need to probably become practiced at it. The reason why I say we're not done is that this was the condition for the net force to equal 0. This is not the answer. We wanted the minimum force necessary to start the box into motion, which means the actual answer is either equals, that would be minimum, or if I want to argue that it needs to be broken loose, then it must be greater than that. That will be the one that will start getting into motion. The smallest force necessary is the one that's right there and greater than that. You're the one who has to kind of interpret what you get for your answer. By saying net force equals 0, and getting this as our answer, we know that every force that's equal to that or less will ensure that the box doesn't move. So we need to be greater than that. Again, not a lot new here, but boy, it feels rough, doesn't it? That's a lot. And I don't care who you are. I know that I make this look a little bit easier, but I've been doing this a long time. There's a lot to keep track of in problems like this. And, you know, just looking at all the things that had to be done to get here, there's a lot. But I don't shy away from it. I think you guys are capable. I just know this takes practice. You understand now why I was so insistent on getting your pictures right. Right? You see what I mean when I say putting the angle someplace wrong, what happens? Everything's messed up. But it really just switches sine and cosine later. The real problem is if you don't include one of the forces correctly. And there's something else here that's not being talked about. And I don't know if you really understand this, but I just made this up. But this has to be true, right? If you don't know why I wrote this, you should. Because this is the threshold at which when I pull, I lift the box off the ground. If the upward part of this force is greater than the weight of the box is no longer touching the floor. And I'm not making that up. That's when the normal force goes to 0. So there's lots of other things to read here that might not be obvious. If I really wanted to check something out, I would try and do another problem with you guys where I push the force this way. You know, pushing down on the box increases friction. There might be a minimum force that has to be applied so you can even still move the box. I don't know. There's also things like solve for the coefficient that will be low enough to get the box to move. Or what coefficient has to be great enough to keep the box in place. These are all the same problem. Your job is still to figure out the net force equations for X and Y, and then use them in your quest for trying to figure out what are they asking me to do. There's a problem on your practice test, and it's also in your homework. And I want to just be clear about it, because it's going to come up tomorrow, because everybody's going to have to do it on their practice test. And it's a problem where you're told to apply a force this way in order to move the box up the ramp. You apply a horizontal force. I bring it up because if you look at the forces now, you've got forces that kind of look like this. Do you see what I'm saying? This force, mg, normal friction. You're still going to want to make, you're still going to want to make this your x direction. You really are. But you have two forces to resolve. This one's top level challenging, I think. I put on your practice test because I wouldn't put it on your actual test.